Light
Oh,
moves at
yes.
c with respect to any given observer that you might choose.
Yes,
That's what
and
the
yes.
standard wisdom is. And
Mhm.
all I'm saying is I'm saying that is a convention. It hasn't been proven because we've never observed the one-way speed of light. That is a convention that yields results that work as part of special relativity. It is not the known fact of what is truly going on.
In 1725, James Bradley conducted an experiment that was attempted by two other scientists on different occasions. The experiment was to measure the parallax of a fixed star in order to prove the Copernican model. The first attempt was done by Hooke, but Hooke's telescope did not have enough power to properly observe parallax. Hooke, however, left instructions in the failed experiment's paper, which could be followed to construct a telescope of sufficient power. The second attempt was conducted by Bradley's friend Samuel Molyneux, with Bradley helping him. However, Molyneux unfortunately died, and so, in honor of his dear friend, Bradley made the third attempt at the experiment. All three men chose the same star, Gamma Draconis, the head of the Dragon constellation. The star was chosen for the reason that it never sets in England, the country of its measurement, and it passes directly overhead at some point of the day or night. Molyneux's telescope was built to Hooke's description, but Bradley had to have a smaller one constructed after Molyneux died in order to fit it into his observatory. The experiment was to detect stellar parallax, which is an apparent change in the position of a star due to the relative position of the Earth as it orbits the Sun. Bradley expected to find he would have to move his telescope in a circle as Earth circled the Sun, as that motion would make it look like the star is moving in a small circle. What Bradley found, however, was that he would have to move the telescope only half of the year. For one part of the year, the telescope had to be pointing slightly in one direction, hitting a maximum of 20 arc seconds. Then it would return back to 0 arc seconds 4 months later. Then, 4 months later again, he needed to move the telescope to a maximum of 20 arc seconds in the opposite direction. And again, 4 months later, it returned back to 0. And then 4 more, and back to the 20 arc seconds in the first direction. This observations of Bradley's was given a new term, called stellar aberration. And Bradley explained it with a simple analogy. If rain is falling straight down, a man standing still in the rain would see it fall straight down. And if the man jumps straight up and down, he will still see the rain fall straight down. But if the man walks perpendicular to the falling rain, he will have to tilt his umbrella in the direction of his motion, in order to stay dry. This is caused by the same Galilean effect as dropping a cannonball from the mast. If the raindrop is 10 feet away when it is at eye level, and is at 0 feet away when it is at foot level, then it appears that the raindrop has moved towards you at a slope. You don't have to worry so much about the rain that is currently above your head, as it will be behind you before it can hit you. This also means that it is the velocity of the observer that causes this apparent position of the star, not the observer's position, which would have been parallax. In September, the Earth is moving at its most perpendicular to the parallel light rays of Gamma Draconis to the north, and the telescope needs to be tilted a tiny amount towards the north. To get an idea of the small amount of tilt, here is a 20 arc second difference, and here is a degree difference. In December, Bradley's zenith is moving towards the star and is parallel with the light rays, and therefore the telescope can see the star at 0 arc seconds from zenith. In March, the Earth is moving perpendicular, in the opposite direction it was from September, and the telescope needs to be tilted in the opposite direction from the September measurements. In June, the Earth is moving away, in parallel with the light rays, and the telescope can again see the star at 0 arc seconds. Bradley explained the results of his experiments with the corpuscular theory of light, as the light was acting similar to raindrops falling. Using this idea, Bradley, in 1728, was able to make speed of light measurements, which were relatively close to the ones we know today. But more than that, Bradley discovered that the speed of light was a constant, as light from every star arrived at the same velocity. It may not seem like it today, but this discovery had profound implications. The idea that the speed of light didn't appear to change meant that the ether is stationary in the Earth's frame of reference, which is strange as the Earth is always changing directions as it orbits the Sun. The effects of aberration will not be explained for another 200 years, and all those years are spent trying to explain how to fit stellar aberration into the other theories.